Okay.
So first off, I'm going to go over a brief overview of pySPEDAS. Then we're going to talk even more briefly about the development schedule. And then we're going to dive into actually developing pySPEDAS tools. And as part of that, I'm going to give an overview of pyTplot, which is kind of the central to all the pySPEDAS. Then I'm going to talk about pySPEDAS load retain architecture. And I'm going to use ERG as an example for most of this throughout. And then I'm going to talk about documentation, how we do documentation, and then show how to work with GitHub and to actually deploy to our repository. Then I'm going to talk about how we're doing examples with Jupyter notebooks and just how to get started there. And then I'm going to talk about how we're doing testing, including unit tests in Python, how we're measuring code coverage, and how we're doing validation tests in IDL. So that is like how we're actually making sure that the data products in IDL match the data products in Python. And if you have any questions, feel free to unmute yourself and ask throughout the presentation, or you can save them and email me afterwards. I'm going to put this presentation on our spedas.org website. And of course, my email is at the first page. I think most of you probably already have access to my email address.
Okay, thank you.
So right now we're using Python 3.6 and later. And the thing to note about this is we're probably going to end up dropping Python 3.6 support soon. The reason being some of our libraries are in the process of dropping. Some of the libraries that we depend on are in the process of dropping that older version of Python. I think 3.6 just became 5 years old, and the libraries that we depend on really only, or it just turned 5 years old, and the libraries that we depend on only support for the last 5 years. So soon this will be 3.7 most likely. And we're using an MIT license. This is just open source. You can read it online. It's essentially free open source. So anyone can download it and use it. And contribute to it. And we're trying to make it a cross-platform. It should work on Windows, Linux, and Mac OS. And we're distributing it on GitHub. And that's essentially what we're treating as the bleeding edge. So all the development is out in the open on GitHub. And I'll go over GitHub later. And we're also using pyPI for releases. This is the standard Python packaging index. And we do pyPI releases not as often as we update the GitHub. So every few weeks to every month or so, just depending on what updates we've actually gotten in there. And so pySPEDAS currently supports loading data from 24 projects covering more than 130 instruments. And internally, pySPEDAS uses pyTplot to actually load the data into variables and create plots. They have their own GitHub page. It's under the Maven SDC page. And they also have documentation at pytplot.readthedocs.io. So we can go here and see. They have a bunch of documentation, including how to actually work with, how to set options and work with pyTplot. And I'll show some examples later of actually using this. And pyTplot currently supports CDFs, NetCDFs, IDL save files, and STS files. I think that's a Maven data format. And in some places, we also use pandas to load some ASCII data sets, particularly for MMS. So if there are any ASCII data files that you need to load, I can point you to examples for using pandas to get that into pyTplot. So here's a list of the missions supported. We're trying to add as many missions as possible. And the thing to note is that while we can load the CDFs from most instruments on these missions, the post-processing of the data products for most missions aren't at the same level as our IDL tools. The exception being really MMS. For the most part, MMS is has the ability to load the same data products as we do in IDL. And I also included a list of all the instruments that we have support for. And right now, I mentioned in an email that the HEP and the XEP are having trouble actually loading the variables in the tplot variables. So I need to look into that. But we have these other instruments like the Verase, the magnetic field, the orbit data, the LEP-E and LEP-I, and the MEP-E and MEP-I, as well as the plasma wave experiment. And so installing pySPEDAS, just to get started, once you actually install Python, it's just a matter of typing pip install pySPEDAS. And if you already have pySPEDAS installed and you want to get the latest version, you'll have to use -- upgrade in the command. And so it's super easy to actually just get started with loading or actually installing pySPEDAS. And this should work on every platform with Python installed, Windows, Linux, and Mac. And an important thing to note is by default, the data are placed in the directory where pySPEDAS is installed. So you can configure this with the SPEDAS data directory environment variable. So if you want to change the SPEDAS data during, you want to change the location where the data are actually placed for all missions, you just set the SPEDAS data dir environment variable. And most missions have their own environment variable. For example, you can set MMS data dir or ERG data dir, and it'll override whatever SPEDAS data dir is. And these environment variables also work with their latest IDL versions. So if you load data in IDL, pySPEDAS should be able to automatically find them. And I'm not sure if that's true for ERG yet. We'll probably have to work with you to actually get SPEDAS data dir and make sure ERG data dir actually work. But they definitely work for MMS and I think MS, most other missions. And data are actually loaded by functions that follow the general form pySPEDAS.mission.instrument. It's a little different than how we do things in IDL. The reason we have like ERG_load_MGF in IDL is because of the single namespace. But Python really doesn't have this problem, so we can have pySPEDAS for MMS, it's just MMS.FPI. For ERG, it's just pySPEDAS.ERG.MGF for the magnetic field experiment, for example. And the load routines currently support local caching, and that matches the remote directory structure. So if you download data and it doesn't change on the server, it'll pick up the local file and won't bother going out and re-downloading the file. We also support temporary files to avoid issues with partial downloads. So if your internet connection drops while you're doing a download, it won't try to load that bad file the next time you try to do the download. And you should be able to load the data files without an internet connection. And you could also, there's a keyword for downloading the data files without actually loading them into pyTplot variables. We also have support for usernames and passwords using the just standard HTTP authentication. So you should be able to log in and download the data files that are only available to team members. And we also have support for loading the files into just standard NumPy arrays without actually creating tplot variables. And this is useful for debugging if there's a variable that's having trouble, that pyTplot's having trouble loading. This is useful for trying to figure out why it's having trouble there. And we also support grabbing the latest file versions. And I'll show examples of that later. And just like with our IDL routines, the options for the load routines are set with some standard keywords like trange. So you can just specify the start time and the end time, and it'll load. For this example, it's December 15th, all the data for December 15th, 2015. We also have the time clip keyword. You're probably familiar with that one as well. Just tells it to time clip the data down to the requested time range. And most instruments where it makes sense, we have the level keyword for the level, and we have the no tplot keyword. This is the keyword that tells the load routine to load the data into NumPy arrays instead of creating the tplot variables. And we have a download only keyword, which tells the load routine to download the files, but don't load them at all. And in that case, the load routine just returns the local path to the files. We also support the var format keyword, which tells it to limit the variables loaded using Unix style wildcards, or you can just specify the actual variable name. And we have a no update keyword, which tells the load routine to only load the data files if they exist in your local data directory. So it doesn't actually go out and try to download it from the web. And we have the suffix keyword, which appends a suffix to the variable names. I think most of this should be very familiar if you're familiar with the IDL load routines. And to see all the keywords supported by a load routine, you just use the Python help function in Python. So you just open Python and then import pySPEDAS and type help. For example, pySPEDAS.mms.fpi will show all of the keywords. And I'll show how to actually update that documentation later. So here's a real simple example with ERG, magnetic field data. So all I did was install Python and then open Python. Then I typed, after I installed pySPEDAS with the pip install pySPEDAS, I just type import pySPEDAS. And then to load the data, I type pySPEDAS.erg.mgf. And by default, all of these, all of the instruments have a default time range. So if you don't specify a T range keyword, it should just go out and download some data for whatever the default is for that instrument. And I'll show how to change that later. But for this example, it's data on, it's the default data for this instrument is the L2 8-second data on March 2017. So you can see it went out and it downloaded the data, and then it loaded the data into tplot variables. And then to plot the data, all I did was type from pyTplot import tplot, which essentially just imports the tplot function from pyTplot. And I called tplot on one of the variables, which is the, I guess, 8-second magnetic field data in GSM coordinates. And here's an example of the figure it created. So all this should be really familiar to you if you've used IDL or IDL tools. Essentially just you call a function to load some data, it creates the tplot variables, and then you call tplot. Big difference is that you actually have to import the functions to use them. For instance, import pySPEDAS and then import tplot from pyTplot. And it's not shown here, but when you create this figure, it's actually an interactive figure. So you can zoom in, you can move things around. And so that's pretty much all I have for the basic overview of pySPEDAS. That's most of what pySPEDAS is right now. So for the development schedule, we've been doing the core load routine development since 2018, and I expect that to go through at least this year. I think it's getting a lot better, and we're almost there for most stuff. The big thing for ERG is really getting support for the XEP and the HEP data in pyTplot. And once we figure out why those data products aren't loading, I think that's probably one of the biggest hurdles right now. And from 2019 and probably on through at least 2023, we're going to be doing load routine post-processing. This is where the bulk of the work actually exists, I think, for most missions outside of additional analysis tools like 2D slices. And so we've been doing this primarily for MMS. We have most of the load routine post-processing for MMS, and we just started on Themis. So the thing to note is that some missions are further along than others to post-processing. And for example, I mentioned that MMS load routines are mostly done, but we're just getting started with Themis, and others still need to be started. And I did some of the post-processing for ERG magnetic field data. You notice in this figure, it actually has the correct colors and it has the correct labels on the plot, but doesn't have the Y title. I think I'll show this as an example, the internals of this load routine later as an example, but we're also setting the Y-axis range when we load the data. And we started doing coordinate transformations. So we have the core routines for actually doing coordinate transformations as of last year. And those don't currently work with pyTplot variables. So we're gonna have to write wrappers that do the actual, that work on pyTplot variables. But right now we have the core, for instance, GSC to GSM transformations. And we have that code ported over directly from our IDL code. And that's going to be an ongoing task, is implementing coordinate transformations and making it easy to use with pyTplot variables. And we're going to need to, there's going to be additional analysis tools that we're going to be adding starting this year. We already have some basic analysis tools. For instance, we have dynamic power spectra and wavelet transformations. But the big one in here is going to be 2D slices of distribution functions and actually working with distribution functions. So I guess just jumping into pyTplot and giving an overview of pyTplot. So it includes tools for loading the data files into tplot variables and creating plots, as well as setting the metadata on the tplot variables. And all of it is very similar to how it works in IDL. I think they modeled it almost exactly from our IDL or tplot. So for example, it has a CDF to tplot routine, which takes a list of cplot or CDF files and converts them into tplot variables. And there's also, I showed earlier, the tplot function that creates the plots. There's also get_data. Of course, that should be familiar. Same with store_data for actually saving tplot variables. And there's options for setting tplot options, setting options on specific variables. There's also tplot_ options, which allows you to set global options, just like in IDL. And there's also a tplot_ names to list the currently loaded tplot variables. And of course, the big difference between all of these and with IDL is that you actually have to import them from pyTplot before you use them. So for example, to get the data values out of that variable that we plotted earlier, you just type from pyTplot import get_data to bring the get data function into your namespace. And then you call the get data function on the variable that you want to get the data from. So in this case, we return the data in a variable called D. And I just printed the variable by typing D. So this is a named tuple. And so right now the times can be accessed via d.times. I'm thinking about replacing this with d.x. So that it matches more closely with our IDL version. And the data values are d.y. And if this were a spectra, it would also have the energy, or if it were energy spectra, it would have the energy values as d.b. If it's for distribution functions with higher dimensions, we follow the same format or the same naming scheme that we have in IDL. So d.b1, d.b2, d.b3 are all supported. And if you want to create a new variable, I mentioned earlier, stored_data. So you just import that from pyTplot, and you call the store data function. The first argument is just the variable name. So in this example, we're creating a variable named ERG_B field. And then the second argument is the data option. And then you just give it a hash table with X being the times and Y being the data values. And if it's a spectra, you want to do, again, you give it a V for the energy values or the pitch angle values. And again, it supports B1, B2, and B3. So if you have higher dimensional data, you can use store data to create those variables as well. And in this example, I just called tplot on the variable we created, and it created this plot. But notice this time, since I used store data, I didn't use options. I haven't called options yet. It didn't include the labels, and the colors are different. So I guess now we can cover the general SPEDAS load routine architecture. The load routines contain a few core components. The main one is really load.py, which loads the data or downloads the data and then loads the tplot variables. There's also a config.py, and this is mostly right now for setting local data directories, but you can put additional configuration options in config.py. And there's this, what's called the dunder init file. It's just __init__.py. This is required for Python packages. And it's really what allows you to access the load routines using the naming like this, pySPEDAS.erg.mgf. All the load routines also have, or all the packages and missions have a readme.md, which is just the general package documentation. And there's also a folder called tests with a file called tests.py, which have the unit tests. And we'll cover all this soon. For ERG, the instrument-specific load routines are stored in a folder called satellite. Most other missions have these stored in their dunder init file right now, but it's a good idea to have these broken out into their own folders. So I went ahead and did that for ERG. And the instrument load routines all call load.py to do the download and the load the data files. But they essentially just give you a place to put the instrument specific codes, like doing post-processing of the loaded variables. So for instance, on our GitHub page, to access pySPEDAS and to dig around, you just go to github.com/spedas. You can type, just click pySPEDAS, and then click in here, and you see all the different missions. There's ERG, and so there's the README, the init file, the config file, and the load file, and tests is where the unit tests are, and I'll talk more about this later. And in the satellite folder, there should be files for each individual instrument. So for instance, MagGF, the magnetic field data. And I'm gonna go over more about how this works, how it's laid out. So just as an example of the instrument load routine file, this is that mgf.py that I just showed. At the very top of all of them, we have some required imports. I think we're using NumPy for something. I think I'll show that in just a minute. I think we're using that to set the y-axis ranges. But we also need the load routine from the pySPEDAS.erg.load, because that actually does the downloading and the loading into pyTplot. And we also do post-processing, so we need the pyTplot, we need the options function, the clip function, which clips in the y direction, the y limit, to change the y limits, and get data to return some of the data. Then we have the function definition, including defaults for the various keyword options. This is where we set the default T range, as well as the default data type and the default level. And you can update those. And you can see we also support the username and password, time clip, no update, download only, get support data that returns the variables that also returns, it tells the load routine to load the variables that are labeled as support data rather than just data. And then we have below the function definition for all the instruments, we also have a doc string with documentation on the keyword options. And I'll show the importance of this in a little while, but essentially lists all the different keywords and what their options are. So, and just below the doc string, we have a section, and this is just MGF. We have a section where we allow users to set the data types, for instance. And I think I just took this mostly from the ERG_load_MGF, just to show as an example. So the user can specify a data type as 64, which means the 64 hertz data, or 8S, or just 8, says the 8-second, or specifies the 8-second data. And 128 is 128 hertz data, and 256 is 256 hertz data. And then we call the core load routine with all the user's options. And we just specify the instrument and send all the options there. And it goes out and downloads the data and loads them into tplot variables. And if no data were loaded, or the user specified no tplot, or only to just download the data files using the download only keyword, it just returns whatever the load routine, it just returns whatever was returned by the load routine. So if they specified download only, it would just return the files right here. Or if it were none, it would return none. And then we do post-processing of the loaded variables. And again, I took this post-processing from the ERG _load _MGF in IDL. So what we're doing is clipping these variables to -1 to the 6 to +1 to the 6. And then next up, we set the Y range for some of the variables. This is why I imported NumPy earlier. We find the minimum. We set the limit to the minimum and the maximum of each variable. And I think the IDL load routine does the same thing. And then after that, we set some options with the options keyword. So one big difference between pyTplot and IDL-tplot is that we call the labels legend _names. This is essentially just the labels in IDL-tplot. So it puts the BX, BY, and BZ on the right-hand side. And we also then set the color of the label, set the colors. So blue, green, and red. And it's just using the color option. And then we return the variables. And that's pretty much all there is to the MGF load routine right now. I think there's more stuff in there in the IDL version. Yeah, here. So you can see the IDL version has that same custom data type, or flexibility in the data type. And again, here's the clipping with tclip. But we're not printing out things like the PI info and the rules of the road yet. But for the most part, it's very similar, at least for this load routine. And I talked about the load.py. I wanted to go over that file as well, since it's really core to the downloading. So up at the top, we have the required imports. For instance, we import a file called daily names. This is just like file _daily names in IDL. And we import a file called download, which is very similar or almost exactly like SPD _download in IDL. And we import a time clip function. This is just for time clipping the data. And we actually changed the name to tclip here, because there's a function, or there's an argument called time clip. We don't want those to get the function name and the argument, the keyword argument, to actually get confused. And then of course we need the CDF to tplot function from pyTplot to actually load these CDF variables into pyTplot variables. And we need the config file to load or define the local data directories. And you can put other options in the config file as well and just use it throughout. And so we also have the standard function definitions, including the defaults for various keyword options. The big thing here is that we really expect users to load data using the instrument specific calls. So we tell the users that in the doc string with the warning to use the instrument load routines and not call this directory. But below that doc string, We set up the file prefix since it's common to all the various instruments. And then we set up a path format to each data type based on the instrument name. And again, this should be pretty similar to how it works in IDL. The big difference being how times and dates are formatted. And in Python, we use what's called strf time formats. So to get a list of these, there's this useful website called strftime.org. That's pretty much how I always find it. So strf time, and it has a list of the different types of time formats, codes, and what they mean. For instance, this one is the year, and then this is just the month, but with it's always 0 padded. So in this example, you can see this is the year, the month, and the day. And just like in IDL, our download routine supports file versions by just using question marks. So you can put question marks in file versions. And then when you call download, you just say latest version, and it'll download the latest version of the file. And so below all of that, what we do is we call daily names with the file format, with the path format that we created above, and the time range. And that takes the time range and actually creates a list of the data files. As well as it also supports the res keyword, just like in IDL. So I mentioned earlier, this is almost exactly like file_daily names in IDL. And then we pass those remote file names to the download function. And I mentioned earlier, this is almost exactly like the SPD_download in IDL. Even the keywords are the same. So remote file, remote path, local path. I think this should have the same options. And we do sort the files after we download them. And then if the user request sets the only download keyword, it returns the output files. It just returns a list of the files that it downloaded. Otherwise, it continues on and creates the tplot variables by just calling cdf to tplot. And the main argument here is just a list of files. And if the user didn't actually want to create the tplot variables and just wanted to return the data, we just return the data here. This keyword's also passed to the cdf to tplot, and it just returns the data as NumPy arrays stored in hash tables. And then if the user's requested a time clip, or set the time clip keyword to true, it just loops through each variable and does the time clip to the user's start time and end time. So most of this should be very familiar if you use if you develop tools in IDL. We tried to really model it after how we do things in IDL to make it easy to get up and going for Python developers. And I mentioned we're using doc strings to document functions. This makes the documentation available via the help command in Python. So when you create that doc string, like here, when you type help, it'll actually show what's here. So for example, calling help on pySPEDAS.erg.mgf, it lists the function as well as the current defaults for the function and gives a brief overview. This function loads data from the MGF experiment from a Rosse mission, and then it lists all the parameters. And we'll probably have to update this, for example, to set the data types. We don't actually have the valid options listed yet, or the valid options for the levels listed yet. And I think we're missing documentation for the username and password options. And at the bottom, it just says that what it returns, which is a list of the variables created. And that's assuming you don't use this no tplot keyword. And so doing the doc strings like this also allows us to generate the HTML documentation of pySPEDAS automatically using a tool called Sphinx. But we haven't put this together yet. It's on the to-do list. Should take like an afternoon or so, and it'll be available for all the missions. But this is essentially how pyTplot generates their documentation. This is just coming directly from their doc strings. And this is all generated with Sphinx. So eventually we're going to have essentially what has the pySPEDAS.erg.mgf and then have the options and the list of the parameters. And all of that will be documented or come directly from these doc strings. That way, when you update the doc string, it updates the documentation in HTML. It's one of the really good things about Python is that there's so much infrastructure for doing development already. It makes doing all this stuff really easy. It'd be pretty difficult in IDL. And we're also creating top-level documentation with these readme.md files. And these will also be used by Sphinx for documentation. And so, for example, I've been using, and also the readme.md files are always rendered when you look at GitHub for the page. So this README is always rendered down here below the list of files. So you can see we have a brief overview of MMS, and then we have a list of the instruments, and then all of the features that are included. And then we have some examples. And I imagine we should really have, I need to update this to include acknowledgements as well as a few other things. But yeah, I just wanted to show this as an example of a README file. It's actually populated. I think the current one for ERG is kind of lacking. It really just has the magnetic field experiment listed and an MGF example. But so we're gonna have to update this to list the other instruments. But the other instruments do actually work. We have the, for instance, lep_i function. So you can call pySPEDAS.erg.lep_i to load that, the low energy ion data. But this one doesn't have the post-processing set yet, like the MGF one does. And these documentation, these files are actually created using Markdown. So if you're not familiar with Markdown, it's just I suggest just Googling when you get to updating documentation to use Markdown. It's just really a syntax for generating files, text files. So as I mentioned before, we're using GitHub for our bleeding edge. It's just github.com/speedas/pySPEDAS. And we also have repos for the examples, which can be found by browsing our top level organization. So it's just github.com/speedas. So for example, we have a repo called MMS-examples that contains all the MMS examples. And all of these are Jupyter notebooks, which I'm also going to talk about later. But just as an example, I clicked on one of the Jupyter notebooks and it rendered it. So this is an example of calculating plasma beta, the FGM and FPI data. And so it shows step-by-step how to do calculations, how to load the data, how to create plots. I can show that real quick as well. We could show some more. So MMS examples. So if you have a lot of examples, we can always create a top-level repository called, for example, arase-examples. And these have readmes as well, which allow you to render images that show the output of the examples. And so, for instance, the one over here, plasma beta, just click plasma beta and it renders it. So we load the FGM and FPI data, and we do some interpolations, get them all at the same timestamps, and then we calculate magnetic pressure and then plasma pressure, and then we do the division, and then we create the variables. So it's all fairly straightforward. I think this is essentially how we're doing crib sheets, but I think they're probably better than crib sheets because they allow they allow you to actually do additional text and and allow you to send it. It's clearer because there's also like formatting, like having some things larger than others, some text larger than others. So you can really emphasize things. So to actually start working with GitHub, I really took the perspective here that most people aren't familiar with GitHub. So I'm sorry if you already are. I'm going to show you how to actually get started with working with pySPEDAS on GitHub. So you start by just creating a fork of the project, and that's clicking this fork up in the upper right-hand corner. And this creates a copy of pySPEDAS under your GitHub account. So mine is supervised, and it created a pySPEDAS-1 because I already have a pySPEDAS under mine. And the big thing to note here is that it says this current status of how this is linked to the main pySPEDAS, right? So at this point, it's even with the pySPEDAS, but if someone updates pySPEDAS, the actual official repository, while you're working on it, it'll say that you're behind, and I'll show how to sync up in a few minutes. But once you have a copy of or a fork of pySPEDAS under your GitHub account, you can then download the code to your local machine using Open with GitHub Desktop. And if you don't have GitHub Desktop 2, it'll prompt you to download it here when you click it. So it's essentially you just click the code button and then Open with GitHub Desktop. And once you have it installed, it'll show, it'll open this prompt where essentially you just set your local path of where you want to store pySPEDAS locally, and you click clone. And so then you just, it downloads your local, it downloads to that folder. So from this example, it downloaded a full copy of the pySPEDAS repository to pySPEDAS-1 folder. And then you make changes locally, and then they'll show up in GitHub Desktop. This is what GitHub Desktop looks like. So for example, I changed the readme.md file. Previously, it listed the instrument as just MGF. I updated it to magnetic field experiment. And so once I saved it, the changes showed up in GitHub Desktop. And when you're ready to commit the changes to GitHub, you just select the files you want to submit. And you do that on the right here on the left-hand side. And then you describe the changes on the bottom left-hand side, and then click commit to master. And if you just update one file, it'll usually just do update in the file name. But if you have multiple files, you'll have to actually give it a description or a custom name and a description of the changes you make. And then you click push to origin. Once you click the commit to master, it'll update this upper right-hand corner to say that there's changes that need to be pushed back upstream. And once you click push to origin, that should send the changes to your fork on GitHub. And then this is updated. It says the branch is one commit ahead of the main of the main official copy of pySPEDAS. And you'll also see your copy of or your changes in the distribution. And then when you want to send the changes to the official pySPEDAS repo, you click pull request. So again, just pull request right here. You can also click compare to see the changes of the differences between your branch, your local branch, and the official repository. And so when you click pull request, it'll show you a list of the changes and let you compare. So you really want to double check the changes you're making, and then click create pull request. And then you can, it'll allow you to update the description. For the most part, I think it just takes the update from, or it takes the description from what you put in GitHub Desktop earlier. So you can also modify it here when you send it upstream to the official repository. And there's a bunch of other stuff here, like you can set reviewers, like if you want someone to check your code before it's actually merged into the official repository. You can actually select users to do reviews, like code reviews. Otherwise, you could just click create pull request. And once you click that final create pull request, your changes are available under the pull request tab under the official pySPEDAS repo. So on this screenshot, we're back in the official pySPEDAS repo, and it just created a pull request under the pull request tab. It has the description and the name. And then to actually merge that pull request into the official repository, you just click merge pull request. And once merged, the changes should be in the repo. So once you click that merge pull request, it updates the file, and you can see here it updated the README. And you can find a list of all the history or all the changes by clicking history. So in the upper right-hand corner of all the different folders, there's a history button, and that lists all of the essentially the history for that folder. If you do history on pySPEDAS, it'll do the history for all of the projects and all of the instrument or all of the missions. But if you just do it on ERG, it'll show the history just under the ERG folder. And all of these are clickable, so you can click on, for instance, update README, and it'll show the changes that were made in that pull request. And there's also a comments thing section down here where you can make comments on updates. And the user should get emails about these comments. So it's good for discussing changes. And so when someone makes a change to pySPEDAS while you're working on it, your branch might be behind the main one. And that'll come up again in this status here. So this branch is one commit behind. This happened after I merged that pull request. So to sync the changes, you have to do it on your local machine first. You just type git pull upstream master, and you run that in the directory where your local pySPEDAS fork is. So this is, in my example, it's just the pySPEDAS-1 directory. I type git pull upstream master. And you should automatically get Git when you install the GitHub desktop. So this should just work on all platforms. And so once that's updated locally, you're essentially pulling the changes to your local computer from the upstream, from the official repository. Then you have to just use GitHub desktop to push them to your to the local version, to your version on GitHub. So then you just click push to origin, and then you can go back to your version on GitHub or your fork, and it should say it's even with the official repository. So that's most of what you need to actually just deploy to GitHub and work with our repository. I think there can be issues if you modify something that someone else is working on. You could have conflicts, and then when you do the merging, you'll have to work with work with GitHub to actually, with the GitHub interface to merge the changes. But for the most part, we don't really have people working on the same files at the same time yet, so we don't really run into that very often or at all, really. And so for examples, I mentioned we use Jupyter notebooks. To install Jupyter, once you have Python installed, it's just a matter of typing pip install notebook, and then you create notebooks using the command Jupyter notebook. It opens a notebook editor in your browser, so you can then create new notebooks, open old notebooks. It's very intuitive to work with Jupyter notebooks. So I suggest just trying it out and getting started. That's pretty much all I did. They also had documentation on how to use it on their read the docs page. But I suggest just installing pip or installing it and then opening it. And I think it'll be pretty obvious how to use it. At least it was for me. So on to tests. These are we use unit tests in Python to check to make sure that things actually work. So we'll make sure that the load routines actually load data. And these are stored in the tests folder in a file called tests.py. And we're using a framework that's shipped with Python called unit tests. And in pySPEDAS, we have a utility called data exists to check if a variable exists. And so what we do, so there are a couple of tests that are failing right now for ERG. And I mentioned this earlier about the HEP and the XEP, because for some reason pyTplot can't support those files yet. And I need to fix that. But we test, for example, for the orbit data. The big thing here is that all of these methods have to be called test underscore and then something. They always have to start with tests if you're not familiar with unit tests. But either way, you can really just copy and paste the way things work here to create more unit tests or add to them. So I can also show this for ERG, because there's should be tests for every load routine that we have so far. So for the ERG unit tests, we have the orbit data. And right now, by default, the orbit data loads the L3 data. I think we're going to have to update that to also support the L2 data, which we'll have to add or change the path formats based on level. So we also have a unit test for MGF and the LEP-E data, the LEP-I data, the medium energy data, medium energy ion data, and the plasma wave experiment. And I think there are a few different data types. And I tried to name follow really the naming convention used in IDL for loading these different data types. And the really important thing about working with these unit tests is they all have to start with test underscore. And these tests are actually ran every time we commit code to the master branch on GitHub. So whenever you type, or whenever you hit merge, it automatically creates a virtual machine in the cloud and installs Python, installs pySPEDAS, and then runs all of the unit tests for all of pySPEDAS. And the current status for all the pySPEDAS unit tests can be found on the main page. So you can just go to pySPEDAS. At the very top of the README, there's a badge, which is clickable. And right now, all the tests are passing that we don't have commented out. So you can see a list of all of the commits that we've made and the results of the tests. So when I ran this test, or when I committed this change here, test failed for some reason. And I had to make an update to make the test pass. And clicking the status takes you to GitHub actions. So from the top level, you can click this badge to get there, or you can just click GitHub actions. And it should list all of the test runs. And then when you click on a particular test run, you can see the output of the test, how long it took the test to run for the whole package. And then you can click on the job on the left-hand side to actually get the full output from all the tests. So this includes what each test did. So if a test is failing, it'll tell you in here which one is failing. And you get the full output. You can also click over here to download the raw logs. So when a test is failing, I usually just click the log to get the raw log and then go all the way down to the bottom, because it usually stops, it halts whenever a test fails. So the failed test should be in the last few lines and show exactly where it's failing. You can also run these tests locally. It's just a matter of typing python -m and then a path to the actual tests, and Python will run the tests on your local machine as well. And I showed this example. And these unit tests also measure code coverage. So this is how many lines and what lines exactly were executed by the tests. So the current code coverage for all pySPEDAS unit tests can be located on that by that next badge called code coverage. So for instance, we should be at 82% code coverage. I think a lot of Maven isn't being tested right now, but most load routines actually do test the vast majority of their code or execute the vast majority of their code. And when you click on that badge, it takes you to a page called coveralls.io, which shows the status of our coverage. So for instance, it shows, and what this is the code coverage over time. And we're up to 82%. And to see the code coverage for individual files, you can expand the file tree down here at the bottom. So for instance, here you can see each mission. Then I mentioned earlier that Maven still has a lot that hasn't been tested, but most others are above 90%. So you can then drill all the way down to satellite and see that, for instance, MGF isn't being all executed. And you can click on the individual files, and that'll show you which lines were executed by the tests and which weren't. So for in this example, we didn't set the data type to 8S or 8, so it never entered this part of the if statement, actually never executed any of this if statement. So that's why the tests for MGF are only at 88%. We didn't actually execute those lines. And this is useful for figuring out which lines haven't been executed by the test suite, because there could be errors in those lines that just aren't. The test could be passing, but there could be errors in those lines because we're just not executing those lines from the tests. And for validation tests in IDL, I'm using MGUnit. It's actually deployed with pySPEDAS, has been for a while, to build these unit tests. I've been deploying a unit test, and it's a very similar system to using how we're doing unit tests in Python. So for an example of using MMS, we have the MMS Python validation UT defined. And we also have a function called SPD run py validation that runs a Python script and checks that a list of variables loaded actually matches those in IDL. So I have an example here, but it's probably better to just look at the file. So, in IDL. So we have all of these. It's essentially an object called MMS Python validation UT, and then underscore define. And then the methods on the object, again, they all have to start with test underscore, and then you give them a name. And first off, they load data in IDL. And then, so for example, let's do a simple example with FGM data. We load some FGM data, and then we set up a Python script just as a list of commands. So we import the FGM load routine, and then we call the FGM load routine with the same arguments. And then we set, we also have to set a pass or a list of variables that we want to check. So in this example, we're checking the GSC variables and the GSM variables, and then we just pass those to this function. And it returns 0 if there was a failure, they don't match, and it returns 1 if they do. And there are options in here, which can be found at the top of the routine. For instance, tolerance, because sometimes you can have differences due to precision differences in IDL and Python. So you have to set a tolerance. You can change set a custom directory where Python is actually located. And essentially what this routine does is create a Python script and then runs it and then checks the variables. But it doesn't check every single data point. It only checks a number of data points. By default, I think it's, yeah, defaults to 10. So if you have a variable with 100 data points, it'll be every 10 data points will be checked. And you can, of course, change this in your argument or in your calls to SPD run validation. And you can see we have a whole lot of these for MMS. I think all instruments, most data types, we actually have covered to make sure that they actually match, that the data products actually match an IDL in Python. And then to run these, once you're in this framework, all you have to do is type MG unit, give it the object name, and then specify a file name for the output of the tests. And it creates, after it runs it, it creates this file. So in this example, it's Python validation.txt, and it has a list of the test names and whether or not they passed, and then how long it took for that test to actually run. So in this case, we have 3 tests that are failing. This is because I need to make some updates to pyTplot, and we recently updated the EIS routines in IDL and Python. And so I need to go, and that led to the tests failing for some reason. So I need to look into why that is for EIS. But all the other tests are still passing. So that's the end. That's all I have. Unless there are questions. Of course, you can always email me. I'm going to put this on speedas.org.
Okay, so somebody had a question to Eric.
Hi, this is Tom Hori speaking. I have a couple of questions.
Yeah.
Okay, anyway, hi, Eric.
Hello.
How are you doing?
Good.
Okay, I have a couple of questions. One of the question is about the future perspective of post-processing stuff. I think the post-processing stuff includes, of course, just post-processing about tplot variable. And also, it also includes the development of some high-level applications to manipulate tplot variable or multiple data variables. So as I heard, as the first part of your talk, you are planning to, you have been working on the development of some distribution function slicer type application now. So do you have any plans to develop some applications similar to the pod products?
Yes. Let's get to the schedule. So for the part products, I was imagining that being part of the analysis tools. And I hope to get to it to actually start doing 2D slices this year. And I think the part products would be soon as well. So to answer your question, yes, I think we're probably going to start with MMS first, but it's going to be essentially a similar thing with the load routines, where we make it where it's where there's essentially a template and you can just copy and paste, and it should just be very easy to build from it. And I started looking into it a while ago, but I haven't gotten back to it. We've been trying to add more missions and doing the simpler post-processing right now. But it is coming this year.
Okay, so basically you guys are developing the 2D slicer first.
Yes.
Then maybe move on to the pod products. So does that mean that 2D slicer type application is high demanding for MMS community?
Yeah, that the reason I planned on doing 2D slices first is because that's the one I get most questions about. And since they already released data products that are generated from essentially what the part products already produces, I think the slices are really what they're looking forward to.
Okay, so I have another question, which is about how to use the mean, how you're using GitHub. So, don't you guys use any other branch other than master?
So not right now. We really just use master. And
yeah, looks like.
And we create forks in our local copy, on our local account to make changes. Although a lot of times I just commit directly to master.
Okay, yeah, I think it's okay right now. But if in the future, multiple groups participant in development pySPEDAS here, then I think the different group are editing different part of this SPEDAS distribution. So it might be better to use branch. For example, maybe ERG, people use some, well, but so if we have some updates about script for ERG, then we can make a new branch, then commit the changes to that branch, then I think, and then I think we send a pull request to you or whatever, whoever.
Yeah, we could set up a branch for ERG. We could definitely do that. That's actually a really great idea. I'll take a note to mention that to the team. See if we can go ahead and do that.
Mm-hmm. And also last question, actually this is not a question, but comments about error when we load the HCP data and XCP data of ERG. Yeah, actually I did try the ERG. Sorry, I just tried pySPEDAS ERG HCP on my PC now, and I got errors. This reads, let's see, X and V do not match, something like that.
Yeah, I think there's something strange about those files, or at least the data type that's not supported by pyTplot yet.
Well, I'm not 100% sure, but my hunch is that maybe, V element of tplot variable HCP is not a one-dimensional array, but two-dimensional. Yeah, and the number of energy channel times 2, the upper and lower limits of energy.
Yeah, that's probably what's causing the problem.
I guess so.
So I think we really just have to update pyTplot to support those variables in that format of variable.
Oh, do we have to modify pyTplot for that case?
Probably.
Yeah, I'm not sure about the detail about pyTplot, but because I'm just a beginner level user of Python.
Yeah, I think it's probably a change just in pyTplot.
Oh, okay. Okay, that's it from me. Thank you.
Yep, thanks.
Okay, so any other question from Harase colleagues? Eric, so thank you very much for the nice tutorial stuff. And I have a question. So actually the current ideal ERG plugin for SPEDAS to provide the rules load and acknowledgement when user download the CDF file data. So actually the load procedure includes such the message. So how can we include such the rules load for the pySPEDAS?
So the metadata in pySPEDAS should be there, including the global attributes. But how to access that, I'm not sure off the top of my head. I would have to look into it. So what I'm going to do is update our load routine to actually do that for the MGF data. I think that would be a good example. Because right now we don't have that, but it's essentially just, I need to look into how to do it and then update this so that it has it prints it at the bottom like it does in the IDL routine.
Okay.
And then that way you guys can just copy that way. But it should be available. The global attribute should be available through the pyTplot variables. I'm just not sure how to access it off the top of my head.
Okay, so I understand. So if the the pySPEDAS make a handle, so the global G attribute, the CD, that will be convenient. So okay, I understand.
Yes.
Okay.
I think that's where it pulls it from now.
Okay.
In IDO.
Okay. Yeah. So any other questions? Eric, and also can we also make sense the schedule for the development of pySPEDAS and IDL the SPEDAS. So actually today that you show us the schedule for the pySPEDAS development for the next couple of years. So how about IDL SPEDAS?
So I think IDL is we're gonna slowly move away from that as more and more developers use Python.
Okay.
But I'm not sure how that looks. Like Jim Lewis is probably a better person Jim Lewis and Vasilis. They're probably a better person to ask about the IDL schedule.
Okay.
But I suspect over the next 4 years, I know a lot of people are starting to use Python and pySPEDAS.
Yeah.
Especially with everyone in the US anyways working from home. A lot of people have been having trouble with their IDL licenses. So it's really getting more and more usage.
Oh, that is a good motivation to use Python. Okay, yeah. So actually, currently the many ERG colleagues and also the other researchers have used the IDL SPEDAS to get the RSA the data for the analysis. But often somebody asks us when they can use the pySPEDAS or that they cannot use the IDL SPEDAS. So this is a very critical, essential question for users and also to us. So probably we'll continue the plugin, ERG plugin for IDL SPEDAS for a while. And also we should catch up and we should develop the necessary routing for the pySPEDAS. So I'll ask Vasilis how he thinks about the future plan, but I understand the current situation.
And one thing to note is that once we have these validation tests for ERG, this will give you a lot more confidence in the Python. Once we have we actually can test that the data products in IDL and the data products in Python match and can do that all automatically. It gives you a lot more confidence in the Python stuff.
Okay.
Once that's available, then you'll have a lot of confidence in being able to actually tell people that they can use either or, as long as those particular tests for that particular instrument and data type are still passing.
Okay. Okay, any other questions?
And I mentioned earlier that you can always email me if you do have questions afterwards.
Okay. Thank you very much.
I'm always available. And so thanks for calling in.
And later, could you send us this slide?
Oh, yes, yes.
Can we share with our colleagues?
Absolutely.
Okay, thank you very much. That's very helpful.
Great, thanks for calling.
Yeah.
Okay, so everybody okay? Okay, Eric, thank you very much. So the very nice tutorial stuff, we understand very much. Thank you very much. And please keep in touch.
Oh yeah, for sure. Thank you.
Yeah, please. Thank you.
Thank you very much.
Bye-bye.
Bye-bye.
Thank you.
Bye.
Bye.